Okay, let's see if we can work out what the physics is of the accretion disk. Now what we have is a red star and a white dwarf. The white dwarf was originally a star, came to the end of its life, had a planetary nebula, left a white dwarf behind, and now the smaller star has also come to the end of its life later, and matter starts falling, it starts expanding, and matter falls through the Roche saddle and then comes in towards the star. It doesn't fall in directly because the whole thing's rotating, so it'll end up doing a fall in, loop round, and then smash into itself here. Maybe it'll get through a bit and bounce around. And so you're going to get a whole bunch of smashing around going, and eventually you'll end up with a disk, or not a disk, a ring of a particular width of gas around it, around the white dwarf. And as more and more matter falls in, this donut or disk will get more and more massive. Now what's going to happen in that disk? Well, remember, all parts of the disk are going to be spinning round, so the centrifugal force balances gravity as usual for an orbit. But the inner part of this ring, it's closer to the white dwarf, so gravity is stronger, so it would have to rotate faster, so the inner bit's going faster than the outer bit. But that means if you've got gas going very fast on the inner part of the ring and gas going slower on the outer part of the ring, you're going to get friction between the two, fluid friction, which is called viscosity. What that's going to do is it's going to slow down the fastest gas and speed up the slowest gas. So as the inner gas gets slower, that means it will actually spiral in. And as the outer gas gets faster, it'll go out. So what you're going to start off with is a white dwarf and a ring. But as time goes on, the inside of the ring is going to move in, and the outside is going to go out and out. Till eventually you end up not with a ring but with a disk. And at some point the center will touch the surface of the white dwarf, and at that point we will have also the hotspot's going to be moving outwards, so you're going to have a hotspot here as the gas comes in, and then a disk going all the way from there down to the center. And that's what our accretion disk looks like. Now, one thing we can ask for the accretion disk is how bright will it be? Why would it be shining? We can see the thing, it must be very bright. Well, what's happening, of course, is that things are falling. As they fall, they must get rid of their potential energy. So we know that gravitational potential energy is given by minus g mass in the middle, the white dwarf, the mass of the object that's falling in over r. So if you plot the radius here against u, we get the curve we've seen before looking like this. So the material starts quite a long way out at the hot spot and then moves in until it reaches the surface of the star down there. So this here is the change in gravitational potential energy, and that's the amount of energy liberated by each kilogram of matter as it falls in. So what have we got here? We've got that the energy per unit mass falling in is equal to the Gm white dwarf mass of the thing that's falling in. We've got 1 over the radius of the white dwarf, that's the end state, take away 1 over the radius of the whole disk, the initial state. Now this is going to be about 10 to the 9 meters, because we know that's roughly how far apart these things are going to be. Roughly. This is a very approximate calculation we're doing here, just to get the rough orders of magnitude of the different sizes. Whereas this is going to be 1 over, say, 5,000 kilometers, that being the radius of the white dwarf. So in practice we can ignore that, it's 1,000 times smaller than this. This is the energy. What we really want is the power, so that's per unit time. So the power is just going to be Gm white dwarf, and the mass per unit time, which is written m dot. So that's not just the mass of one lump falling, it's how much mass falls in per second, all over r, the white dwarf. So that's how much power we'd expect. And it depends on something we don't know, which is the rate at which mass is falling through the hotspot and spiraling in through the disk. But of course we can turn this upside down. If we measure the power, which is the luminosity of the white dwarf, of the accretion disk around the white dwarf, and we know everything else here, we can work out m dot. So we get that m dot equals the power observed times the radius of the white dwarf over g times the mass of the white dwarf. So if we give a one solar mass white dwarf, we know observationally that the powers of white dwarfs is about, luminosity is about 10 to the 27 watts. So if we plug the numbers in, we end up with a rate at which mass is falling in of 3 by 10 to the 13 kilograms per second. So that's an interesting number. Sounds pretty big. That's 30 trillion kilograms a second, 30 billion tons a second. But you compare that to the mass of the star. Mass of the star is 10 to the 30 kilograms. So that means you can run for of order 10 to the 17 seconds, which is like over 1 billion years at this rate. So that's a lot of mass falling in. The red star's not going to run out of mass anytime soon. It's actually a very, very small fraction of the red star's mass. So these things can keep going for a very long time, just 1 billion years at this rate, far longer than the red star is likely to remain a red star. So, okay, these things can last long. That's good to know, because we know these variables have been, individual ones of them have been seen for at least 200 years. But there's another thing we can work out. What is the temperature of one of these things? Now what we've got is a disk which has an area of roughly pi rd squared. Of course there's the middle of the disk which isn't radiating, but that's very small compared to the outer radius. That's a rough size. All the mass is hitting the outside and working its way in. As it works in, it has to get rid of its energy. Remember, it's moving from here to here, so every time it goes in, it has to get rid of more and more energy. It can't just leave all the energy till the end. It has to get rid of it gradually as it goes in. How's it doing that? Well, the inner fast-moving parts here are rubbing against the outer slow-moving parts, and that friction generates heat, as friction normally does, and that causes everything to glow. So let's say the whole thing is heated up by this friction to some temperature T. The amount of energy radiated, given by the Stefan-Boltzmann equation, the power radiated equals the area, Stefan-Boltzmann constant, T to the 4th power. And that must be equal to the luminosity, which is given by this equation up here. So that equals G m white dwarf m dot over the radius of the white dwarf. So if we plug in the area here, we end up calculating that the temperature is equal to the 4th root of G m white dwarf m dot, the rate at which matter is falling in, over pi r d squared r white dwarf. Now I should emphasize that this is a very rough calculation. We're assuming, for example, that all parts of the disk are the same temperature, and as you know, we did a number of approximations further up. But it gives us a rough order. For 3 by 10 to the 13 kilograms per second falling in, give it a radius of the disk of about 10 to the 9 meters, and a mass of the white dwarf of the solar mass. That comes out as about 9,000 Kelvin. Pretty hot, so it's going to look quite blue. But in fact, that's an underestimate of the true temperature of what we're going to see. You have to bear in mind that the gas is starting here, and as it starts to move in, the slope of this graph is quite gentle. As it gets closer and closer, the slope gets steeper. So that means the amount of energy you liberate in the outer parts of the disk per unit radius is less than the amount of energy liberated in the inner parts. So you're going to get most energy has to come out in the inner parts compared to the outer parts. Okay, so we have to get rid of more energy from here, but also the inner parts have a much smaller area. So if they've got to get rid of more energy in a smaller area, how do they do that? Well, the only way is to get hotter. So what you're actually going to see is the inner parts of the disk have got to be extremely hot, much more than our average temperature, whereas the outer bits are going to be much cooler. So the spectrum you're going to get, if you plot the flux against the wavelength, the inner parts are going to be extremely hot, so they're going to peak down here at very short wavelengths, and they're going to radiate a lot of power. Then as you go further out, it won't be so hot anymore, and so it'll radiating less power, so it'll radiate less power, which at a lower temperature, so it peaks a bit further out. And then right to the outer parts of the disk, it's going to radiate even less power and at much longer wavelengths because it's cooler. So if you add these all together, you're going to get a spectrum that looks something like that. A sort of smooth, steady rise and then a big peak well into the ultraviolet. And indeed, that's exactly what you see for these things. It's a general feature of accretion disks that you get what's called a power law spectrum like this. So it all seems to hang together. Gas is falling in. Viscosity makes the disk expand. It's dumping stuff on the surface. Some of the radiation actually may just come from the stuff falling on the surface because it was probably moving pretty fast by the time it hits there. So it turns out actually about half the luminosity comes from the surface and not from the disk at all. But the disk comes into equilibrium as matter falls in. It generates power. And a rough calculation, very crude, indicates that we need mass infall rates of a few by 10 to the 13 kilograms per second. Which means that this can go on for a long time. Factoring that in, we get an average temperature of about 9,000 Kelvin. But in practice, that's an average. They'll be much hotter in the middle and much cooler at the outside, and the overall effect will give us a blue ultraviolet peaking spectrum, just as we observe